Hello, welcome to this Math Bay video on Law of Sines Part 2 on how to solve the tree on a hill problem. I would like to start by saying this is a problem that I acquired from a colleague earlier, and it's a pretty neat way that you can apply the law of sines. So we're going to work on it together now. And here's the situation. It's a nice application problem. The oldest and tallest tree in a national park is to be advertised in a brochure with comments about its remarkable height. Your job is to calculate the height of the tree given the following information. First of all, the tree stands vertical on a hill that's sloping up at 12 degrees from the horizontal. So we're talking about a 12-degree angle of elevation, which we have previously discussed. So that's the angle right there, 12 degrees. Secondly, at a certain time of day, when the sun is at an angle of elevation of 80 degrees, the tree casts a shadow down the hill. Sometimes the shadow will be cast up the hill, but the shadow is cast downhill from the sun and makes a 30-foot shadow. So I'm going to put 30 feet for that shadow. Okay. And the angle of elevation of the sun is 80 degrees. Now here's the part that a lot of people typically will get wrong. They will tend to put the angle of elevation in the wrong place. So if this is 30 feet right here, they'll say the angle of elevation is 80 right here. But if you remember, an angle of elevation is always from the horizontal. So it's actually this entire angle, which is 80 degrees. And since due to corresponding angles, this is 12 degrees, we can subtract from 80 and get that this is 68 degrees. That's the part that we need here. Okay. So that angle actually in our triangle here is 68 degrees. All right, so if we're looking over this, we have a non-right triangle right here that we're focusing on. That's the triangle that we're focusing on right here. And we know a 68-degree angle and a 30 feet. We're asked to find the height of the tree. So I'm going to go ahead and put an X right here since we're trying to find that. And we need more information. We need another angle in this triangle. And the angle we need is right here because it's opposite the 30 feet. The 68 is opposite the X. So I already know in terms of my sine function, it's going to be sine of 68 over X. Solving this is easy. It's setting it up. Then it's going to be sine of something else over 30, the opposite side, but I got to work around to find out what this is. The whole trick to this problem is going to the base of the tree and drawing in another horizontal line. Okay, and using the fact that we have that 12-degree angle here, a 12-degree angle here, and so we're going to have another corresponding 12-degree angle right there. And if that angle is 12, its vertical angle is also 12, and this angle here from the tree to the horizontal is 90, which means this entire angle right here is 90 plus 12, or 102 degrees. So now I have a triangle that I know two of the angles in. If I draw the triangle a little bit more like this, I know this bottom one is 68. I know this one now is 102. So the top angle, by subtracting from 180, is only 10 degrees. And now I can finish off my law of sines. Sine of 10. 30 sine 68 equals x sine 10. So x is equal to 30 sine 68 over sine 10. When you multiply and divide that in the calculator, x is about 160.2. It's really 160.18, but that's 160.2 feet rounded to the nearest tenth. And that's the tree on a hill problem. For our next example, we're going to do one where the shadow is cast uphill. So, what if the shadow was cast uphill and you had to calculate the height of an object? We're going to draw our own picture this time. There's a flagpole on a hill sloping up at 10 degrees. So here we go. Flagpole on a hill that slopes at 10 degrees. At a certain time of day, the angle of elevation to the sun is measured to be 65 degrees. Okay, I'm going to draw my flagpole on the hill. Okay, and here's my flagpole. And the shadow is cast up the hill at 10 feet long. Okay, so we have a 10-degree angle and a 10-foot shadow. That's a lot of 10s. Now, if the shadow is cast uphill, that would mean the sun is on this side shining. So here's our Mr. Sunshine casting a shadow with the ray of sun, and there's that situation. All right, we want to find the height of the flagpole, and we have currently no angles, so let's get some angles. The angle of elevation to the sun is 65 degrees. Now, this is going to be a little bit different because remember, angle of elevation is always from the horizontal, which means this angle is 65 degrees. So we're going to have to work with that. Again, my corresponding angles from the bottom angle being 10 degrees, I know this angle is 10 degrees. And I know this angle is 10 degrees, which means all these corresponding angles being equal, also the vertical angles are equal. So now I have a 75-degree angle here inside the triangle. So part of my law of sines is sine of 75 over x. Now, I know the 10. I need this angle up here so that I can finish sine of that angle over 10. Well, let's see. This is a 90-degree angle between the horizontal and the vertical flagpole, which means the angle in the triangle is 80. So I have a degree angle of 80 and 75 with my 65 and 10 together. I will just subtract from 180. And I get remaining 25 degrees when I take 180 and subtract the 80 and subtract the 75. I get 25 for up here. So now I can finish my law of sines. Putting that 25 degrees over, x is equal to 10 sine 75 over sine 25. So I will take the calculator, which I've been kind of doing on the side because it's not working out so well. 10 sine 75, finding just the right angle, and then I'm going to divide it by sine of 25. And I get about 22.9 feet tall for the flagpole. Tomorrow I'll give you a couple of practice problems on these to work on your own, or I'll put them on the website. But that's the end of this lesson on how to solve the flagpole, tree, or any vertical object on a hill with law of sines.